So we're going to get chapter 13 under our belt today. Chemical equilibrium. Like I mentioned for the last chapter, we do chemical kinetics first because chemical equilibrium is dependent upon kinetics. In other words, the speed of a reaction is integral to understanding chemical equilibrium. Let's see if I can make sense of that. Well, let's look at a little history first. The two, kinetics and equilibrium, developed almost simultaneously in the 19th century. But the treatment of the mathematical treatment of kinetics required some more advanced math that didn't develop quite as quickly. Equilibrium, they were able to understand it mathematically earlier than kinetics. So what do we mean by chemical equilibrium? Well, we know equilibrium can come in many forms. It can be chemical, it can be physical as well. And I think we introduced that topic in chapter 10 and 11 when we were looking at the vapor pressure of liquid in an enclosed vessel. As the material, the liquid, evaporates, in the beginning, it only goes one way. It's just vaporization. But eventually, you build up enough molecules of the vapor in that space to where they start to return in a condensation step. And once you reach the same rate of evaporation and condensation, you get a physical equilibrium. We can use that idea in chemical equilibrium in terms of a reaction where you have some reactants and they go one way to begin with, but eventually you build up enough over here that the return reaction is also a possibility. And when you have a rate going this way, and we could say our a rate constant for this one, and we have a rate constant for this one. And so it goes this way at a certain rate and return at a rate. And when those two rates are equal, you have equilibrium. Now, what we notice is that on a macroscopic scale, we see a disappearance of reactants to produce products, and eventually you have a concentration of reactants and a concentration of products, and they don't change. That's where the equilibrium idea comes in. But they don't change because they're being created as fast as they are being depleted. So on the macroscopic scale, there's no change. But on the microscopic scale, the activity is furious, forwards and backwards. So it's a dynamic situation as opposed to a static. I've asked you this question before. Has anybody taken Kayla's talk? You want to say something, Kayla? Also, Margaret present.
I didn't realize my thing was not.
Either I can't hear her or somebody else is in the room. That happens. If you've had physics before, physics can be divided into two categories. One is statics and one is dynamics. Statics is where there's no motion at all. So that's like an example would be a seesaw, right? The balance is static. There's no movement. Where you have, if the seesaw is a type of lever, right? You have a force on this side and a force on that side, and if the torque on one side balances the torque on the other side, there's no motion, right? But if you're like Young Frankenstein, where a little girl sitting on her seesaw and the creature sits down on the other side, pops her out and she ends up through the window in her bed. And her parents are pleased to see her in bed. Only she was out there with the monster for a while. Nobody's seen the Young Frankenstein, have you? You ought to. It's hilarious. Okay. So after all of that, this boils down into a macroscopic static situation. It appears static, but microscopically it's very dynamic. And that's where an understanding of kinetics comes in. This is another way to represent it over time. You will see, get my cursor down here. You'll see, for this reaction, you'll have nitrogen, hydrogen, and nitrogen here. And you'll have no products, no ammonia. But gradually you build up a concentration of ammonia and you deplete nitrogen and hydrogen until you reach equilibrium and we don't see any change in concentration. Right? And it's always based on the concentration, not on absolute amounts. Now, I will say that we use absolute amounts sometimes when it's convenient for calculation purposes, but for the chemistry, it's all based on concentration. And it's either molarity, which we assign like this, so the concentration at equilibrium would be A with square brackets. Right? If it's not at equilibrium, we'll use parentheses. If we use molarity is this option. The other option is if all of your reactants and products are gases, sometimes it's more convenient to use partial pressures. Right? In that case, instead of this, we'll use partial pressure of A. And there's no equivalent for this one. You just have to know whether it's at equilibrium or not. And if it's not at equilibrium, then we have another situation that we have to deal with, and that'll come in just a few minutes. Okay. This is just a reiteration of the fact that we're getting a handle on the kinetics first before we approach equilibrium. Another way to look at it is reaction rates, right? The reaction rate in the beginning, the forward rate is everything. This is where we do our initial rates calculations. We approach a reaction from the initial rates because we have no competing reverse rates to interfere with the forward reaction. But in reality, we start to build up and we get a significant reverse rate, and the forward and reverse rates are now equal. Okay, so let's look at this one. The next couple of slides are useful for preparing for the lab. Right? We're not going to name it yet, but in fact, we're introducing the topic of Le Chatelier's principle. So if we have this reaction where we've got water and carbon monoxide, and it's in equilibrium with hydrogen gas and carbon dioxide. These are all gases. If it is at equilibrium, and then we add some of this, right? We add water vapor to the reaction mixture. What's going to happen? We have increased the concentration of water molecules. So our collision model, our kinetics collision model says there are going to be more frequent collisions between water and the carbon monoxide that's left. So that means we're going to increase the rate of the reaction, right? We've increased this concentration. So this rate is going to increase and produce more of these. So the reverse reaction will eventually increase until it realizes a balance again. Right? So what we're actually doing is shifting the reaction toward the products by adding this reactant. Now, as a practical matter, when we calculate the concentrations of each one of these again, after it reaches the second equilibrium, then the amount that we added here will be depleted, but it will be higher than the original equilibrium because you won't use all of it. In other words, it's going to consume some of what we added. It's going to consume some of this that's left. So this will be depleted. So overall, this will be an increase. This will be a decrease. This will be an increase for the second equilibrium. That's known as an equilibrium position. The positions can change, but the equilibrium itself is established one way or another. Right? So what if we add more hydrogen instead of this one? We add hydrogen. Right? Same argument applies. We've got more collisions between the hydrogen and the carbon dioxide at equilibrium. So the reaction speeds up to the left until you get enough of these to speed up to the right, and they balance again. Okay. So if we're going to quantify equilibrium, we need this law. It's called the law of mass action. It was proposed by two Norwegian chemists in the middle 19th century, Peter Wade and Cato Goldberg, who was his brother-in-law. And this is what they came up with. Well, actually, they approached this problem looking at it in terms of what drives chemical reactions, and they wanted a description for it. And as so often happens, when you start an investigation, you're trying to answer a question, as often as not, it takes you off in a completely different direction. So that's why scientists need open minds to be able to latch on to serendipitous moments. So they eventually decided that you could approach reactions in terms of their dynamics, reaction rates, or their statics, the equilibrium. So at this time, there were a lot more. These weren't the only guys that were working on, the only people that were working on kinetics versus equilibrium. So they were in constant contact with their peers. And actually, during the middle 19th century, Norway and Sweden were very active in chemistry, extremely active. Lots of good work came out of both countries. Denmark too. So they expressed things in terms of concentration because they were interested in solutions. All right, so here's what they came up with for this law of mass action. It just says that for that reaction, this constant at a given temperature, at a fixed temperature. If you change the temperature, then that changes. But as long as the temperature is constant, then this is constant. And at equilibrium, you have the product concentrations, right? Each to the power of its coefficient, divided by the reactant coefficients, reactant concentrations to their respective coefficients. So there's a fundamental difference between the law of mass action and rate laws. Right? The law of mass action does incorporate the coefficients of a balanced equation. So that means if you want to write this expression, you've got to balance the equation first. Then you can write the rate law. You can write the mass action law. Now, these are concentrations. So what we discover is that if the reactants or products, any one of them, is a solid, then that factor does not enter in here. Say if C were a solid, then it would disappear. Wouldn't even put it in the expression. If it's a gas or if it's a solution, it goes in. If it's a solid or if it's a pure liquid, like if we had one of them were liquid water, then it would go away. Any pure substance, any solids do not find a place in the mass action law for that reaction. Now, how you deal with that difference is up to you. Some people like to say, well, those factors are incorporated in this constant. They're just inconstant. Some people are okay with saying, no, they just disappear. But we don't write them in there. The other thing we don't do is we don't put units for the K. We don't have units. And the reason for that should become obvious. If this is molarity, and this is a 2, and that's a 3, and this is a 1, and that's a 4, those powers could jumble all around. And you could have the sky's the limit for units for the K. So we just avoid that confusion and don't write units for K, and we're very meticulous about setting up the expression. And if you do that, then any solution to the problem will give you the right units. So we have to take extra care. And if you go to any reference manual and you look up the K value for a particular reaction, the only thing it's going to tell you is the original units for concentrations are either molarity or partial pressure. That's all it's going to tell you. It's not going to have any units for the K values at all. Now, of course, the value for K will be different. If we have an expression here for that, then this one for partial pressure would be like P of C to the C power and P of D to the D power divided by P of A to the A power and P of B to the B power. These two values are not the same because these units are not the same. They are related, and we're going to get to that in just a few minutes. You can interconvert them. There's a formula for that. But just purely writing the expression, they are separate and not equal. Okay, so if we write a K, a law of mass action for a particular balanced equation for a reaction, but we need to use Hess's law to combine equations to get a target equation, which we did in the first semester. What do you do with the K values? If you have a K for one reaction and a K for the second reaction, and you rearrange them however you need to add them together to your target reaction, what becomes of the K? Well, first of all, if you do anything to that equation, you have to do something to the K. And these are the rules. If you have to flip the equation, if you have to invert it, then the K becomes an inverse. It's 1 over K. Because now you've got these, instead of these as reactants, now they're products, and these are reactants. So that inverts the K. So invert the equation, invert the K. If you multiply the equation by a factor, like you need 2 of them, so you multiply the whole thing through by 2, what does that do to the K? Well, the new K is going to be K to the second power. It's going to be K to that power. And let me see if I've got that animated. If I don't, then put it on the board. No, I don't. Okay, so if we have an equation here with, let's see. Yeah. Well, let me write out the whole equation. Let's see, we have a dying marker. Okay, we have B, equilibrium with C, and D. Okay, we multiply that times a factor. Let's make something up, say 3. Right? So now it becomes 3A, 3B, 3C, and 3D, right? Okay, so what does that do to the expression? Well, instead of A, now this is 3A, and this is 3B, and this is 3D, and this is 3C, right? So the mathematical rules for powers say these are all raised to the same third power. That's the same thing as saying that whole thing to the third power. So that's why the new K is to the third power. Okay, those are the first two rules. Flip the equation, invert K, multiply by a constant. That's the power of K. Then what do you do? Let me see. I'm gonna steal my own thunder. Then what do you do if you add two equations together with a K1 and a K2? If you add those equations together, your new K is K1 times K2. Now remember, if we were doing enthalpies, like delta H's for them, you just add the delta H's together. But if you're doing an equilibrium, then it's the product of the K's. So those are the three fundamental rules for manipulating equations and adding equations together. All right. K never changes for a given temperature, no matter how much of each reactant you use. It'll reach equilibrium, and the concentrations then placed into that mass action equation will always give you the same K for the same temperature. So we don't call it a K for nothing. It's a constant. But those concentration values can be all over the place. You can start off with a lot of reactants, and eventually it'll reach equilibrium. Put those concentrations in the equation, it gives you a K. You can start off with very little amount of A, and maybe a whole lot of products, and eventually they'll reach equilibrium. Those values go into the equation to give you the same K. But they arrive at equilibrium at a different position, different concentrations. They're still at equilibrium, but the position is different. And that concept is very useful when we talk about acids and bases later, and buffer factors. Okay. So when we write K's, some of them have special meaning, right? If we just write a K, then that could be confusing. So in general, we would write KEQ for equilibrium K, because we've got K's here and we've got K's there. K's are all over the place. So this is an equilibrium K. But there's a very special one, KW, that's assigned to the dissociation of water. We haven't talked about that yet, but water, pure water, will dissociate into hydrogen ions and hydroxyl ions. Not many of them, right? But enough to establish an equilibrium, and we give that a KW. So that's a special reserved for water. There's also one for Ka, and that's for any acid dissociation. So we have hydrogen chloride gas. We dissolve it in water, and it dissociates. or a better example would be a weak acid like acetic acid, right? Vinegar. Put it in water, it partially dissociates, sets up an equilibrium between the undissociated acid and the hydrogen ions plus the acetate ion. So we give that a Ka for that value. If it's a base, a weak base, right, we would say Kb. Right? It's not up there, but it's just as valid. Ksp, we're going to talk about that one later. Solubility product, right? When you put a very sparingly soluble salt, which in the past we've called insoluble, but in fact, many insolubles are sparingly soluble. So they set up an equilibrium also, and they have their Ks, solubility product. And then we have other Ks like this one, the formation constant for complex species. So if we take silver ions in solution, we can put them in solution as silver nitrate, that's soluble. And then if we add chloride to it, right, silver and chlorine are going to come together and drop out, precipitate. We want to get that silver back into solution, well, add ammonia. And silver and ammonia will form a complex that's soluble. And the K associated with that equilibrium is Kf. We'll talk about that in much more detail later, in a later chapter. And then there's Kp, and we talked about that one a little bit earlier. This is if the equilibrium concentrations are in terms of gas partial pressures. Then it has a Kp. There are others, but these are the most common that you will encounter. All right, so here we have the Haber-Bosch equation. Make ammonia from nitrogen gas and hydrogen gas. And if we express things in partial pressures, you have the expression on the left, Kp. The partial pressure of ammonia is to the second power because its coefficient is 2. And then the denominator is your reactants with partial pressure of nitrogen, first power, partial pressure of hydrogen, third power. And that's your Kp for that expression. If we express it in molarity, then you have the right-hand expression, and it will be a completely different number. K and Kp are not the same, but they are related. Here, this slide, we're going to calculate the K using these equilibrium partial pressures in atmospheres. Okay. So there's our expression. We set it up first, then we plug in the numbers. So the partial pressure of ammonia is 2.9 times 10 to the minus second atmospheres. And nitrogen is 8.9 10 to the minus 1, and hydrogen is 2.9 times 10 to the minus 3 to the third power. And we calculate that value, and we get 3.9 times 10 to the fourth is our K for partial pressure for that equation. And now let me see. Let me look ahead a little bit. Yeah, so the next slide is going to convert that to molarity. Okay. So there's our expression. If we know Kp, then K, actually, I would write KEQ here. And then it's the gas constant. And since this is in atmospheres, that one is in our 0.08206 liter atmospheres per mole K would be this value. And then our temperature in Kelvin. And then this is a change in moles. So if we have, we're going from nitrogen gas, hydrogen gas, and we're in equilibrium with ammonia. Right? So we have 2 here and 3 here. Then what's the change in the number of moles? We went from total of 4 moles here of gas to 2 moles here. Right? So remember, when we have a delta, it's always final minus initial. So it's 2 minus 4. So this delta N is minus 4 for this equation. Okay. So we need to know that from the balanced equation. We need to know the temperature in Kelvin, and we need to know the gas constant. And then whichever one of these we have, we can solve for the other one. Okay. All right. We're going to do one. So using that value for Kp, all right, we plug it in there on the left. Then we leave this one as our unknown. We're given this one, and this is occurring at 35 degrees, which is, that's not really the Haber process. He pumped things up to about 400 degrees Celsius. But at 35, you have 308 K, and then minus 4 for that. And we solve for K. Right? We have an equation and one unknown, we can solve for it. So the K in, if the values are in molarity, the K will be 2.5 times 10 to the 7th. And we didn't have to have molarity to do it. Right? We had partial pressures first. And then we did need to know the temperature. And then we solve for the KEQ. So we can use that for any mass action equation in terms of molarity. We can use that new value for K. Okay. So one of the last things we talked about in chapter 12 was catalysts. There were homogeneous catalysts and there were heterogeneous catalysts. Well, we're going to ride that horse again. Homo versus heterogeneous equilibria. Homogeneous equilibria is which all of the reactants and products are in the same phase. Okay. So that first one, everything's in the gas phase. It's homogeneous. Second one, everything is aqueous. Like HCN or hydrocyanic acid dissociates into hydrogen ions and cyanide ions in solution. And that is also homogeneous equilibrium. A heterogeneous involves two or more different phases. Now, if we write the K expression for the top one, K is going to be, let's say we use partial pressure of oxygen to the third power. That's it, right? Because the other two are solids, right? And you can't tell from this whether it's heterogeneous or homogeneous because you don't have access to the equation, right? But if you know the equation is that one, we can say it's heterogeneous. The second one, we would write that one where water is split to make hydrogen gas and oxygen gas, right? We would write that K, and this, I should put KP here. We would write that K in terms of gas, would be probably the best way. So that would be the partial pressure of hydrogen gas to the second power times the partial pressure of oxygen gas to the first power. And that would be the expression for that second equation. And you can't tell from that it's heterogeneous. You need the equation to tell. All right. This just restates what I mentioned earlier. Now, if we write that equation, and if we write the law of mass action in terms of molarity, which you can do that for a gas, so many moles per liter, then the K would be square brackets O2 to the third power. Right? And we could interchange that value with that value by using our previous equation. All right. So what can we learn from K? We've learned how to write K expressions. equilibrium expressions for an equation. But what does the K tell us? Well, if we've got reactants yielding products, and we write the expression here, put C and oops, B, and then the reactants go in the denominator. Then what can we say about that if we know that the K is a very large number? A very large number means that the reaction favors, at equilibrium, favors products. Very large K means lots of product. Very small K means this is large and that's small. So that favors reactants. Right? Now your book is going to tell you if it's exactly equal to 1, then it favors neither one. But I don't buy that because you've got these powers in here. Right? If each of the powers is 1, 1, 1, 1, 1, yeah, then 1 for a KQ would be right. It would be perfectly balanced. But with these different powers in here, you can't say it's exactly 1 is the ideal for a balanced, an equal amount of reactants, equal amount of products. So that's why I say if it's very large, that way. If it's very small, this way. If it's near 1, it's somewhat balanced, right, between reactants and products, but you can't say exactly how much. Right, so if it's very large, the reaction essentially goes to completion. You don't have much reactant left at all. And if it's very small, it doesn't even want to go, right? And that was the problem that that Haber faced when he was trying to develop the reaction of nitrogen and hydrogen, right? The equilibrium constant was very low for the temperatures he needed. Right? We calculated it was fairly large for a low temperature, 35 degrees. It was like 10 to the 4th, something. Right, so it favored products. The problem is the reaction rate was so slow. Right? It may favor the products, but it'll take you centuries to get there. Right? That's the difference between kinetics and equilibrium. Is equilibrium only concerns itself with the ends of that curve. Right? Remember the reaction curve like that. Equilibrium only is interested in the end parts, whereas kinetics is interested in this part. How fast does it go? So that was the problem that Haber faced. And he eventually solved it, obviously. Okay, so if the reaction lies to the right, the value of K should be large or much greater than 1. And actually, I probably should need about 3 of those right carets. And if it lies to the left, the K would be very small. Okay. Now I mentioned earlier, what if, let's see, I'm gonna leave that alone for now. What if you start off not at equilibrium, which is where most reactions begin? Right? Can you tell which way the reaction is going to go? That's where this concept of Q comes in. Q is simply this expression, but not equilibrium concentration. So now we use parentheses. Okay, and these are the actual values of concentration before equilibrium is established. So we can calculate Q and we can look up what K is for that particular reaction. And we can compare Q to K. Okay? So there are 3 possibilities. Right? If Q is equal to K, then you set up the reaction so that it's already at equilibrium. Right? If you put certain reactants and certain products together in the same container and you calculate the Q for it, but the Q is equal to K, then you're already at equilibrium. Right? Where's the fun in that? What if Q is greater than K? What does that mean? That means that this is much larger. The ratio here is larger for Q than it is for K, which means this part of the expression is too big and this part's too small. So that means, with that being said, if this is too big, it wants to lose some of these and make some of those, right? So if it loses product, it wants to shift to the left. So your reaction is going to be left shifted to reach equilibrium. And then, of course, the other possibility is that. So if Q is less than K, that means this is too small and that's too big. So that means you don't have enough product, and now it's going to shift to the right. Now, why do we even care? It's not just because I say so. It's because if we want to solve problems, which I'm going to show you how to do that in just a minute, solve equilibrium problems, you need to know which way is the reaction going to move, right, to reach equilibrium. All right, and there it is in black and white and blue. Now, I'll also make this point. If you're going to say a reaction shifts to the right or shifts to the left, if you don't have a balanced equation in front of you that you're referencing, shifting one way or the other, then right and left has no meaning. Because you could just as easily write it in reverse, right? And then shift to the right would be wrong if that was to be the answer. So whenever you say shift to the right, shift to the left, you've got to be able to reference a balanced equation. That's important for this lab. Because some of those questions going to ask you, which way does the reaction move? Right or left? Well, if you say right and you don't have a balanced equation, then how do I know if you're saying the right thing? Write the equation, then reference right or left. Okay, so here we have an example of iron 3 ion plus the thiocyanate. Iron 3 plus and thiocyanate ion combine to produce this complex ion, FeSN SCN2 plus. Right? Okay, so if we have 6 molar iron and 10 molar thiocyanate are mixed at a certain temperature and at equilibrium, the concentration of the product is 4 molar. What's the value for the equilibrium constant? Okay, here's the way I do these. I find it useful, since you got to have a balanced equation anyway, to write the balanced equation with sufficient room so that I can spread the values out underneath it, because we're going to need more than one value, and I'll show why in just a second. Okay, here's our balanced equation, right? Okay, so what are we given? Well, initial concentration is what? 6 molar for this one, right? That's initial. And thiocyanate is 10 molar. Initial. Those are mixed together at a given temperature. What's this one? Initially. It's not a trick question. It's 0, right? You had no product initially. Okay? It's like our initial rates. You don't have any product yet. Okay, then there's going to be a change. Which way is it going to shift? Well, obviously, you don't have any product, it's going to shift to the right. So you don't even have to calculate Q. Right? You know it's going to go to the right. So you're going to produce some of this one over here. And we're going to let that equal X. You're going to add a certain concentration of X over there. Well, what does that mean for these guys? Well, the ratio is 1 to 1 to 1. So if you add an X over there, you're going to lose an X over here in concentration units, molarity, think molarity. And you're going to lose an X over here, right? So what is the situation going to be at equilibrium? Well, this one's going to have X, concentration, molarity. This one's going to have 10 minus X. This one's going to have 6 minus X, molar. Okay, so that's the situation at equilibrium. And this we call an ICE table. Initial change equilibrium. That's extremely useful technique. So let me see. Well, okay. While that's true, they're giving us information there that I didn't take advantage of, did I? Let's see. At equilibrium, the concentration of this one is actually 4. So they told us that this concentration is 4 molar, right? And so we added 4 molar here. Well, what does that mean over here? That means we subtracted 4 molar here, and we subtracted 4 molar here. So what does that mean for this one? 6 minus 4 is what? 2, isn't it? And this one is 10 minus 4, which is 6. Now we have equilibrium concentrations. It's just a simple matter of writing the KEQ. What is it equal to? Well, it's equal to this one to the first power over this one, iron 3 plus to the first power times thiocyanate, the first power. So we can plug in the values, right? We put 4 here, we put 2 here, and we put 6 here. We do that calculation. So 4 divided by 12, right? That's 1/3, isn't it? That's the K value for this equation. Now take the next slide. Shows it. There we go. Now that we know the K, we could do a different problem with different starting points, right? Different equilibrium position. And if we knew where we started from, then we could actually calculate where we end up, because we know this one right here. And we know the relationships of each of the others. Right? So we can solve for that X and find out what that X is. And then we could use that to find out what this is and this is. So now that we know this one, we can say our starting point was different. Say it's a different value here, and I think that's on the next slide. So if we start off with 10 molar here and 8 molar there, yeah, start off with 10. Let's erase that one and that one. That one. So we're going to start off with 10 here and 8 here. Right? And we're beginning with 0 of the product. All right, so now we're going to add X here. We're going to subtract X here. We're going to subtract X here. And the question is, what's the molar concentration at equilibrium of this value? Right? So whenever possible, if you can see far enough ahead, choose your X's, choose your unknowns, so that when you solve for that value, that's your answer. That saves you a step. It's not always possible, but whenever possible, do it. All right, so now we have 10 minus X, we have 8 minus X there. Right? So with the same expression here, now we know that this value is 0.333. Then this value is X. And this value is 10 minus X. And this value is 8 minus. Okay. So now we have to solve for X. All right. Where's the fly in the ointment? Expand this polynomial, right? It's a quadratic. So you're going to get a quadratic out of this, and you're going to have to solve for the X using the quadratic equation. And I think that's in useful information. I'm pretty sure it is. Equations, where are you? There it is. Far lower right-hand corner of the useful information. And I always keep it on the back of my calculator. So if we expand this, what do we get? Well, remember how to expand a polynomial? These two multiply together, these two multiply together, and then let's see. These two multiply together would be 80. These two would be X squared. And then 8X minus 8X and minus 10X. So it'd be minus 18X. Minus 18X. So there would be your expanded polynomial for this expression right here. I find expansion is easier than factoring. You try to find the factor for this one, right? Make these two out of that one. I always found that to be more difficult. But then we would multiply that one, that whole expression, times this one. Right? So 0.333 times 80 is 26.64. 26.64, and that's just a number, right? Because this is just a number. Then 18 times 0.333 is a negative 5.99x. Right, because I'm taking this whole thing over here and multiply by that denominator comes the numerator on this side would be equals. And then this would be plus 0.333x squared equals x. Correct? Okay. So now what we want is everything equal to 0, right? You use the quadratic equation when x squared x and the constant value or the numerical value is equal to 0. Then you can use your quadratic equation. So our quadratic then is going to be 0 equals, let's see, let's put it in order. This is x squared, 0.333 x squared. And then this x is positive on that side, it becomes negative on this side. So a -1 and a -5 is a -6.99. -6.99x. And then 26.64. Okay, there's our quadratic. Now we need the quadratic equation, right? So x is going to be equal to minus b. And for the formula, this is b. This is a, b, c. So it's a minus b, plus or minus
square root of b squared minus 4ac divided by 2a.
Okay. That's the quadratic equation.
So if we put this in here like that,
Squeeze it over here on the side. Still picking it up on the video. Yeah.
we need minus b. So it's minus, and b is a minus 6.99. A plus or minus square root of, and I gotta jump that out there. B squared, so minus 6.99 squared minus 4 times a, which is 0.333, and then times c, times c, which is 26.6. There we go. And that's all divided by 2 times 0.333. I can remember having to prove that in school years ago.
Don't ask me to do it now. All right, so what you'll notice is you're going to get two answers, right? Because this is plus minus. Then you got to decide, yeah, I got to take a back up and look at reality. Which one makes sense as to which one you choose. So if we got 6.99 squared, okay, that's 48.86. And then we're going to subtract this one right here. So 4 enter 0.333 times 26.64 times. That's 35.48 subtracted from the original. Yeah. So inside here, this value is 13.337. 13.376. Okay, so down here we got 2 times 0.33. And this is 0.667. That's because it goes on 333 forever. So we rounded it here. To avoid rounding error, that's why I did that. Okay, so now the first one is going to be plus 6.99 plus 13. So 6.99 enter and 13.376 plus divided by 0.667. The first possibility is 30.53. Or what's the other one? Well, 6.99. Oh, what did I forget to do? I didn't take the square root of that.
Oh, that's how you dropped that.
No, I didn't take the square root of it. So it's let's see, let me go back. Go back to this one. Take the square root. Now 3.657. 3.657. Now we have, okay, so it's 6.99 entered. Add them together first. 3.657 divided by 0.667. There we go. Now this is 15.89. Or the other possibility is 6.99 enter and subtract that. 3.657 subtract divided by 0.667. And this one is 4.997. Okay. X. We're saying that X is equal to this concentration. Right? That's the answer. Okay. Does 15.89 make any sense? Well, let's see. We started off with 10 here. Right? And you're going to subtract. How much can you subtract from 10? 10. That's all you can get.
subtract from that 10 to make X, 10 is as much as you can get. So that one makes no sense. It has to be this one, 4.997 is the value for X. Okay. Now, every equilibrium calculation we do is not necessarily going to be a quadratic. And even if it is a quadratic, we may not have to use the quadratic. If the equilibrium is way over this way, and it only makes a very little tiny bit of this, then its factoring in here is going to be almost nothing compared to this value, right? It's going to subtract almost nothing. So we can throw that one out, and keep this one. So that's what we're going to do in the future, if it's available to us. All right, so come on. There we go. They rounded it 5. Okay. So rather than take the easy route and just slap that up on the board, we went through it the long way. So the rest of them we're going to slap on the board because it takes a while to do these things, especially if you've got to do the quadratic. All right. Yeah, okay. Write it again if I need it. Let me see what's next. You're going to try to do another one. All right. If we get a different equilibrium position, different starting point, we'll have a different equilibrium position. We're going to have the same K. And if we go through all that rigmarole again, we're going to end up instead with 3 mole of iron thiocyanate ion. The difference here is that instead of starting with 10 and 8, we started with 6 and 6. Right? So it makes sense that this is going to be lesser value when we reach equilibrium, because we started off with less. So when we solve equilibrium problems, first rule, balance the equation. The equation must be balanced. Otherwise, you cannot write the equilibrium expression. Then you write the equilibrium expression after that. Then you look at your problem for information that's given to you. Initial concentrations is usually the way it goes. But it could just as easily give you final concentrations, in which case, right, be in great shape. But if you get initial concentrations and you don't have one of them at 0, if one of them is 0, then that tells you automatically which way it's going to shift. If there's a 0 on the product side, it's going to shift that way. If there's 0 on the reactant side, it's going to shift back this way. Then you don't have to do Q's. But if you're given values for all of them, if every reactant and product that you put together in this mixture has a positive concentration value, then you got to calculate Q and compare it to the K to see which way it moves, right? Because our example before had no product, so we had plus X, right? But if we find out that the reaction as set up is going to move to the left, then we're going to have minus X over here somewhere, and it's moving the other direction. Okay, that's why we need Q in those cases. All right. Then you set up, you have your balanced equation, and you set up your ICE table, and you put in the information that's given, and select the X the best way you can. If possible, make sure that the X is the solution to the problem. And if you can't go that route, then try to get X as close to the solution, maybe one step away from it. It takes practice to know which one. If you pick X to be the wrong one, right, and it takes you several extra steps, you should still be able to get to the answer, even if you pick the wrong X. You just got to keep in mind what is the answer, and don't assume that the X that you chose is the answer, right, unless you know it is. Then you substitute those values in the expression and solve the unknown. All right, here are 3 trials. If we have these different values for each one, we're going to have a different equilibrium position, but the K is still 0.333. Right. And if you'd like to work them out, they're the equilibrium. Let's see, those were the equilibrium concentrations. Let's see. Let me go back. Yes. I never noticed that before. Iron thiocyanide ion is given in this expression. So we have to calculate the Q to determine which way it's going. Right? And then solve the problem using the ICE table. And I never noticed this before, but the iron thiocyanate, oh no, the first 2 are equal to 4, and the last one's equal to 6. Okay. Okay. So, what's our objective here? How are we doing on time? Got 25 minutes. Okay, I need to pick up the pace. 2 mole sample of ammonia is introduced into a 1 liter container. So what's its concentration? 2 molar. 2 moles per liter. Okay. At a certain temperature, the ammonia partially dissociates according to this equation. Okay, so this one is going backwards from the Haber process. We flip the equation. So is it balanced? No. You have to balance it first. And then at equilibrium, we're told that 1 mole of ammonia remains. Okay. So we balance that equation. And let's see, on the next slide. Oh, it didn't do it. All right, so if I had time, I'd work that one out for you. But you set up your ICE table with what you know and what you don't know and pick your X. Well, actually, this one should be fairly easy because it tells you at equilibrium you have 1 mole of ammonia remaining. Right? It's like that very first problem we did. If it tells you, if it gives you a value for one of those and you have a balanced equation, you should be able to calculate the others based upon the stoichiometry. So K equals 1.69 in this case. I'm going to have to leave it there. Let's see, dinitrogen tetroxide is placed in a 10-liter vessel. So 1 mole in 10 liters is what molarity? 1 divided by 10, 1/10 is 0.1. Okay, and you're given the K. What's the equilibrium concentration of N2O4 and NO2? Well, you start off with 0.1 molar. And so there's the given stuff. Is the equation balanced? Yeah, it's balanced. We're given the K. And then we set up our equilibrium expression. We'll come back to that one if we have time. But we still have to talk about the Chatelier's principle. Okay, so what's likely part of this setup is that we picked picked X for something, and then we had to use that X to calculate the other one. That's typically the way it goes. Okay, here's Le Chatelier's principle. With Le Chatelier's principle, you're starting at equilibrium. That's your beginning position. Then you're doing something to the system to disturb it. You throw it out of equilibrium somehow. What's it going to do? The system behaves as if it has a brain. It behaves in such a way that it mitigates that change. In other words, it opposes the change. So before, when we said we added some reactant, the system reacted to use some of that reactant to make product until we reestablish equilibrium. Well, you could remove some product. Right? Say we have our nitrogen plus hydrogen yields ammonia. Right? If we remove ammonia, then which way is the reaction going? Going to the right. That's one of the things that Haber used to make the reaction go more efficiently. Right? He had this going at like, I don't know, 400 degrees Celsius. And he also had an iron catalyst in there too, to make it go faster. But what he also did was he bled off in the reaction vessel. He, at a certain rate, he bled off all of the reactants and products. Okay? He took them like that, and he went into a separate stream. Didn't do them all, just took some of them into a separate stream and cooled them. Right? The boiling point of ammonia is a much higher temperature than hydrogen and nitrogen. So he cooled them to a certain point. The ammonia dropped out, and these were still gases. So he extracted the ammonia as a liquid. And then the rest of the nitrogen and the hydrogen, he took that, pumped it back into the reaction vessel. And he just kept doing that. Right? And he got the efficiency up pretty high, over 70%, with several cycles of this cooling. So in that case, he drove the reaction to the right because he was removing some of this, right? When he put it back in here, there was none. There was still some there, but there was less there than before when he pumped this back in. So by removing ammonia, he was driving the reaction to the right, according to Le Chatelier. That's the effect of concentration change on equilibrium. If you change the concentration of any of the reactants or any of the products, after equilibrium is reached, the shift will be away from the added component or toward the removed component in order to reestablish equilibrium. That's the easiest change to understand is concentration. Oh, I got a video.
Le Chatelier's principle states that if you have a reaction to equilibrium and you apply a stress to that equilibrium, the reaction will shift in a direction in order to relieve the stress. We will look at a series of different reaction equilibria. We'll apply a stress to those equilibria and see in which direction they shift. In the reaction between iron plus 3 ion and thiocyanate ion, if we add some iron plus 3 in the form of iron 3 nitrate, and to the iron 3 nitrate add some potassium thiocyanate, the two react to form a reddish-orange complex ion. We filled 2 test tubes with the reaction mixture. We're going to keep one test tube as a control so that we can see what happens to the color. To the other tube, we're going to add some 0.1 molar iron nitrate to increase the concentration of the iron. We see that there's an increase in the dark red color. This indicates an increase in the concentration of the complex ion. This also indicates that the reaction has shifted in the forward direction. As you add reactant to an equilibrium, the reaction shifts in the direction to use up the added reactant, in this case the forward direction. Now we'll add 0.1 molar potassium thiocyanate to the second tube. This increases the concentration of the thiocyanate ion. We see that the reaction mixture turns a darker red color, indicating an increase in the formation of the complex ion. We've added the other reactant, the thiocyanate. The reaction shifts in the forward direction to use up the added reactant. We will now add some 1 molar sodium hydroxide solution. We notice that the red color decreases significantly. This indicates that the reaction equilibrium has shifted in the reverse direction. The hydroxide ion precipitates the iron ion, effectively removing it from the solution. The equilibrium shifts in the reverse direction to try and increase the concentration of the iron. We will now add solid potassium chloride to the solution. We notice the decrease in color, indicating that the reaction has shifted in the reverse direction. The chloride ion forms a complex ion with the iron, effectively tying up the iron concentration. The equilibrium shifts in the reverse direction to try and replace the iron that's been removed. We will now add 0.1 molar silver nitrate to the reaction mixture. We notice the disappearance of the red color, which indicates that the equilibrium has shifted in the reverse direction. We also see the formation of a small amount of white solid. The silver ion reacts with the thiocyanate ion to form slightly soluble silver thiocyanate, which is the white solid. The silver ion removes thiocyanate from solution. The equilibrium shifts in the reverse direction to try and replace the thiocyanate ion that's been removed. We will now add some 0.1 molar mercury 2 nitrate. The mercury plus 2 ion reacts with the thiocyanate ion to form a new complex ion. This effectively reduces the concentration of thiocyanate in the solution. The equilibrium shifts in the reverse direction to try and replace the removed thiocyanate.
So you get an idea of how equilibrium shifts when you disturb the reaction. The first two examples were addition of iron, addition of thiocyanate to produce more of the complex ion, and you get a darker color. But the others, the hydroxyl, the silver, the mercury, the addition of those removes some of the reactants, so it shifts the reaction back the other direction. That's called coupled reactions. So you're interested in one reaction, and you couple another one to it to induce a disturbance in the equilibrium. And there are several of those that we're going to be using in this lab next Thursday. So keep an eye out for those. Also, there's a video discussion of the lab in Brightspace. I think it runs about 24-25 minutes. So it's not too long. And it'll give you a foundation. Okay. So the next possible disturbance, the first one we looked at was concentration. The second one we're going to be interested in is temperature. And we might not have enough time to watch. I've got 2 more videos, but I think we'll have to skip them. And I'll put them in, I'll insert them into the to the recorded video so you can watch it again later if you want. But when we change the temperature, what are we doing? When you change the temperature, you're actually changing K. So the balance of the equilibrium is changed because the K is changed. And the K changes depending on whether the reaction is exothermic
or endothermic. And that's fortunate, because if we have a reaction where we've got some reactants in equilibrium with products, if the reaction is exothermic, where's the heat going? The heat's coming out on this side, right, as a product. So in order to make a judgment call for a temperature change, I look at it in these terms. If it's exothermic, you got heat on this side. So if you increase the temperature, what factor are you increasing? This one. You're driving the reaction backwards. If it's exothermic and you increase the temperature, you're going to favor reactants. Okay, and that was Haber's problem, because nitrogen and hydrogen together to make ammonia is exothermic. But he had to increase the temperature to get more collisions. Okay. So he was faced with a you're damned if you do and damned if you don't. So he increased the temperature to get more collisions for the reactions to go. But he got around that other problem by introducing the catalyst. And the catalyst made the reaction go faster. Right? The equilibrium would be established faster. So when he sucked off sucked off everything and removed some of the product, then he could do that in a timely fashion because the reaction was going really fast. Now, it wasn't going fast enough by itself, but as he cycled through these cooling cycles, then he was able to improve their efficiency. Now, when the reaction is endothermic, then the heat is on this side. Right? This heat goes into the reactants to make product. Right? So if you increase the temperature for an endothermic reaction, you will favor the production of products at equilibrium. Right? That's how I look at temperature. Now, in fact, what we're doing is we're changing the K. Right? So the K for this reaction would do what? If we're favoring products, we would increase the K. Right? But that's for endothermic. But for exothermic, the K, if we increase the temperature, we would favor reactants. Okay, so this effect is due to an increase in temperature. Okay. All right.
This is MSJ Chem. In this video, I'll be looking at Le Chatelier's principle and temperature. Changes in temperature cause a change in the equilibrium position and in the value of the equilibrium constant Kc. Here we have the chemical equation for the Haber process. In the Haber process, nitrogen and hydrogen react together to form ammonia. The forward reaction of the Haber process is exothermic. This can be seen by the negative value for the change in enthalpy. If the forward reaction is exothermic, the reverse reaction is endothermic. We can see this by looking at the sign of the enthalpy change, which is positive. So when we use Le Chatelier's principle to predict in which direction the equilibrium position will shift, we need to know if the forward reaction is endothermic or exothermic. If the forward reaction is exothermic, the reverse reaction is endothermic, and vice versa. Next, we'll predict in which direction the equilibrium position will shift when the temperature is increased. When the temperature is increased, the equilibrium position will shift to the left, which is the reactant side. And the reason for this is that the system will absorb the extra heat, favoring the reverse reaction, because it is endothermic. When the temperature is increased, the reverse reaction will be favored because it absorbs heat. Therefore, the equilibrium position will shift to the left, in the endothermic direction. Next, we'll predict in which direction the equilibrium position will shift when the temperature is decreased. So when the temperature is decreased, the equilibrium position will shift to the right, which is the product side. And the reason for this is that the system will produce heat favoring the forward reaction, because it is exothermic. When the temperature is decreased, the equilibrium position will shift in the exothermic direction, which is to the right. Next, we look at the effect of temperature on the value of the equilibrium constant Kc. So for an exothermic reaction, increasing the temperature shifts the equilibrium position to the left and decreases the value of the Kc. So as we saw in a previous slide, the forward reaction of the Haber process is exothermic. Here we have the equilibrium constant expression for the Haber process. When the equilibrium position shifts to the left, the value of the numerator decreases and the value of the denominator increases. Therefore, the value of the Kc decreases. So an increase in temperature for an exothermic reaction results in a decrease in the value of the Kc. For an endothermic reaction, increasing the temperature shifts the equilibrium position to the right and increases the value of the Kc. Here we have the reaction between hydrogen and carbon dioxide to produce water vapor and carbon monoxide. As we can see from the sign of the enthalpy change, the forward reaction is endothermic. And here we have the equilibrium constant expression for the reaction. When the equilibrium position shifts to the right, the value of the numerator increases and the value of the denominator decreases. Therefore, the value of the Kc increases. So for an endothermic reaction, an increase in temperature results in an increase in the value of the Kc. So let's end with a summary, starting first with exothermic reactions. When the temperature is increased, the equilibrium position shifts to the left and the value of the Kc decreases. And when the temperature is decreased, the equilibrium position shifts to the right and the value of the Kc increases. And finally, for endothermic reactions. When the temperature is increased, the equilibrium position shifts to the right and the value of the Kc increases. And when the temperature is decreased, the equilibrium position shifts to the left and the value of the Kc decreases.
We're going to go to pressure. What effect does pressure have? I got room, I can leave that up there. A pressure change. Right? Does pressure have any effect on liquids or solids? Not really. Right? So if you've got a solution or you've got solids involved and there are no gases, then a change in pressure will have no effect on the equilibrium at all. But if you have gases, then you have to ask yourself, how would the reaction respond to an increase in pressure, say? And how do we increase pressure? According to Boyle, you decrease the volume. You just squeeze it. If you don't want to change the concentrations, then the only way to change the pressure is to change the volume. Right? If you add something to it, then you're getting into this realm, along with this realm. Right? So you're complicating things. So to change the pressure, with gases involved, you squeeze it to make it higher, or you expand it to make it lower. All right, so what effect will that have? Well, it depends. What's the balance? Moles of gas on this side versus moles of gas on this side. If you got the same number of moles on both sides, there will be no effect of pressure by changing volume. There's no advantage to it. There's no way that the system can respond to reduce the pressure. If we increase the pressure, then what's it going to do? Well, it doesn't matter. Right? There's no advantage. But if, say, this side has 2 moles of gas and this side has 4 moles of gas, and we increase the pressure, it's going to reduce the pressure by reducing the number of moles of gas. Right? That's Avogadro's law. We reduce the number of moles of gas favors the reactants. So if the balance is low moles on the reactant side and high moles on the product side, then increasing the pressure will drive it this way. Decreasing the pressure will go the other way. Okay? And it's all in the balance. Which side has the more moles?
The pressure of a system can be changed by either adding or removing a reactant or product, or changing the volume of the reaction vessel. The first point has the effect of increasing the concentration of the reactants or products. The second point refers to Boyle's law. Boyle's law states that pressure and volume are inversely proportional at constant temperature. This can be written in equation form as P times V equals constant K. Changes in volume will affect the pressure of the reaction vessel. For example, if the volume of the reaction vessel is increased, the pressure will decrease. And if the volume of the reaction vessel is decreased, pressure will increase. It should be noted that changes in pressure only have an effect on the equilibrium position when there are different amounts of gaseous molecules in the reactants and products. So next we look at some examples. The reaction we look at is the Haber process, in which nitrogen and hydrogen react together to form ammonia. In this equation we have 4 moles of gas on the reactant side and 2 moles of gas on the product side. This means on the reactant side we have more gaseous molecules, and on the product side we have fewer gaseous molecules. When the position of equilibrium shifts to the side with a fewer number of gaseous molecules, this results in a decrease in pressure. And when the position of equilibrium shifts towards the side with a greater number of gaseous molecules, this results in an increase in pressure. So when we make predictions about in which direction the position of equilibrium will shift for changes in pressure, we need to consider the number of gaseous molecules in the reactants and products. So in the next example, we'll predict in which direction the equilibrium position will shift when the pressure is increased. An increase in pressure shifts the equilibrium position to the right, which is the product side. So the equilibrium position will shift to the right because there are fewer gaseous molecules on the product side, which lowers the pressure. As we saw earlier, there are fewer gaseous molecules on the product side of the equation. When the pressure is increased, the equilibrium position shifts to the side with a fewer gaseous molecules, which has the effect of lowering the pressure of the system. Just like for changes in concentration, changes in pressure do not affect the value of the equilibrium constant Kc. In our next example, we'll predict in which direction the equilibrium position will shift when the pressure is decreased. When the pressure is decreased, the equilibrium position shifts to the left, which is the reactant side. So the equilibrium position will shift to the left because there are more gaseous molecules on the reactant side, which increases the pressure. Because we have more gaseous molecules on the reactant side, an increase in pressure will shift the equilibrium to the left. And once again, the value of the Kc does not change. In our last example, we look at changes in pressure when there are the same number of gaseous molecules in the reactants and products. So in this reaction, we have 2 moles of gas on the reactant side and 2 moles of gas on the product side. So the position of equilibrium will not change because there are the same number of gaseous molecules on both sides of the equation. So if we have equal numbers of gaseous molecules in the reactants and products, changes in pressure have no effect on the position of equilibrium. So let's end with a summary. In this table we have change to the system at equilibrium, change in equilibrium position, and change in the value of the Kc. When the pressure is increased, the equilibrium position shifts to the side with fewer gaseous molecules. When the pressure is decreased, the equilibrium position shifts to the side with more gaseous molecules. And changes in pressure when there's equal numbers of gaseous molecules in the reactants and products has no effect on the equilibrium position. And as we can see, the value of the Kc does not change when changes are made to the pressure of the system.
What we'll do Thursday before we go in the lab is we'll take this review document. I think I used this one. I'm pretty sure I used this one. So I'm not going to throw a curve at you next time. You can study this one. It should be ready for review. Okay. Again, I never did show up. Any questions?